We're going to be looking at ratios, how to write them, a small definition of it, and then a couple of examples. On this first page, you'll see 3 different ways to write a ratio. You can write it using the word 2, 327. You can write it using the semicolon, 827. Or you can be written using a fraction. All 3 of these formats are acceptable ways of writing a ratio. I'm going to start with an example here to show equivalent ratios. This is probably the most common use you'll see of using a ratio. Is setting up, I have 2 proportions right here. One of these proportions is incorrect, and let's talk about why. That will help understand the rules behind equivalent ratios. So if I take a look as to how this 1 went to a 4, and how did this 2 go to 8, and then the secret down here, how did the 1 go to the 4, and how did the 2 move to the 5? In both proportions, the move was done the same way. So let's take a look. On this top one, it looks like from 1 to 4, I'm not quite sure, but let's take a look at 2 to 8. So 1 plus 3 is 4, but 2 plus 3 is not 8. So the other option, it's getting larger, would have to be times 4 up here, which means that 2 times 4 gave me 8. So in this top proportion, it was multiplied. On this bottom proportion, you might have already seen this one was added. So I did plus 3 to give me 4. And slide that down just well. Do that. And this one was also a plus 3 to give me 5. So let's figure out. Up above, we used multiplying. Applying to create an equivalent ratio. Down here they used addition to create an equivalent ratio. So let's see which one is correct. 1/2, is that equivalent to 4/8? Well, it's 4/2 of 8, and I believe so. That is correct. Let's check down here. 1/2 is 4/2 of 5, and it is not. So here's where we find out that this is not, in fact, a true statement when you are doing ratios. When you are creating equivalent ratios, you must use multiplying, or in case, you could also use the inverse, which is dividing. Adding and subtraction are not going to create equivalent ratios. All right, so with that in mind, let's take a look. On this next one, this table shows equivalent ratios to 24 to 40. Fill in the missing values. So here we want to try to take a look and see what's happening from what we're given. How did the 40 go to the 80? And then that's going to help us go from 24 to the next one. So from a previous page, it knows it must be either multiplication or division. It's getting larger, so this one is in fact times 2, which means then this one also must be times 2 to get the equivalent of 24 times 2 of 48. On this next one then, we can go backwards. And then take what we know, the 24 get to 12, and we can also do 12 to 3. So the inverse of multiplying, we know, is division. So let's take a look. 24 divided by what gives me 12? Well, that one was divided by 2. So therefore, 40 divided by 2 would give me 20. If you wanted to look the opposite, you could say 12 times what gave me 24 and kind of fill in the blank from that way. On the last one then, 12 to 3. 12 divided by what gives me 3? Well, in this case, by 4. And therefore, 20 divided by 4 would give me my final answer of 5. And here we have equivalent ratios set all the way up because they're being multiplied or divided. Let's take a look at the last example. Lunara's friends are running a race. Each of them runs at a constant speed. starting at time 0. Which of these tables might show the distance of one of Lunara's friends traveled over time? So let's take a look. This is just going to be our background knowledge of ratios. So we'll use from 3. Whoops, does not look like that is going to work for me. And we'll draw it in. So we're going to go from, here we go. Let's see, 3 to 9 and 2 to 6. What happened on those ones? Well, that was times 3. 3. And this one was also times 3. So far, so good. Wow, this next one, 9 times what is 15? That doesn't help us much. 6 times what is 10? Ooh, what if I did 3 to 15 and skipped over 1 and 2 to 10? What do we notice there? You are correct, they're both times 5. So what can we say about this one? Are they running at a constant speed? That is true. So we can put a little star next to this one. That one is correct so far. That's a possibility. Let's check out this next one. Let's see, 11 to 12, 4 to 5. I can just see right now what's happening. Are they using a multiplication? No, they're using addition, plus 1. We know that addition does not work for equivalent ratios, and therefore table 2 is not going to be an option. Let's check out the next one. I go from 1 to 2, that would be times 2. 1 to 4 would be times 4. Ooh, those ones are not going to work out, so therefore are not going to be equivalent ratios either. Let's check out the last one. Okay, I have 14, 21, and 10 to 15. Okay, 14 times what is 21? That's not going to help me very much at this point. There's nothing, a whole number that I could use. What about, look over here, maybe 10 to 35? Again, that's not going to help me much. What if I went backwards? I see that 14 and 10 are not fully reduced. What if I went and found a smaller version? Could I cut both of these numbers in half? What's half of 14? 7. What's half of 10? 5. So I'm creating for sure an equivalent ratio of the first two. Now let's see if we can connect these to the other ones. 5 times what is 15? That was times 3. 7 times what is 21? That's times 3. 7 times what is 49? That's times 7. 5 times what is 35? Also times 7. So in this case, you could have an option of table 4 as well. So that's our brief overview of ratios and how you can use them in some of the problems you might see.